right, so we got it going here. All right, good morning, good afternoon, and good evening to our India colleagues. Today, we're excited to have a webinar that's going to really talk about how we're moving from our R&D efforts into our test systems as well as our demos. And so I'm going to put the bios in the chat because I want to give our speakers as much time as possible. So I'm going to turn it over to Mike Diedesch from AVISTA to get us going.
All right, thank you very much, Noel. Just audio check, make sure everyone can hear me. We're good? Okay. Yeah, so welcome today. Thanks everyone for attending. Glad to be here today. I'm just going to kick us off and give a quick overview. So if you want to go to the next slide, I can go over the presentation outline. I'll give a quick overview of the test system from AVISTA's perspective in terms of where we're going to deploy this and the scope of what it looks like to do that field deployment. And then most of the presentation will be turned over to the researchers from the 3 universities to talk about their work, their great work that they've done developing these VVC schemes that we're comparing as part of the project. So go ahead and go to the next slide. I'll talk about the field demonstration scope of work. So our goal here is to take the research output in terms of a new method for Volt-Var control that we can use on feeders with high penetration of distributed energy resources and actually put it on a live feeder. We can't deploy all 3, so we have to select one. I say best will be selected, but the reality is the one we select will end up being probably the one that's most easily implemented on our system, given the constraints that we have from a time perspective and budget perspective. So it's not a value statement on which one is optimal, but rather which one is most easily deployed given the infrastructure we've got out there right now. So I wanted to make that clarification. In order to implement any of these Volt-Var control schemes on a live system, one of the key aspects is getting them tested offline first via the offline studies, but then getting them tested in the lab. Because in order to implement it in the field, we have to modify our microgrid controller settings. In the case of this system, our microgrid controller is the system that is actually communicating with the endpoint devices, such as inverters and meters. We want to develop a standard interface for that microgrid controller to also interface with whatever Volt-Var control algorithm is developed at the university level. So we'll bring that all into our lab and test it. In addition to that, there would need to be some modifications to the actual inverter settings themselves, depending on the scheme and how it works. And so we will test that and develop those settings here in our lab as well once we select the VVC scheme that we're going to go with. And then finally, once all the lab testing and validation is done, we'll move it out to the field. So we'll come up with some documentation, get our technicians on board, make sure that they are comfortable with the test plans and trained up on how all these systems will work and how to commission them. And then we'll move it into the field. And so I'm really excited for this. I just want to thank 3 universities. It's been really fun to work with all of you. And I think everyone on the call today will see that they've done some really amazing work. And it's truly meaningful to us as a utility, and I believe to the whole industry, to have these new ideas around what we can do in the future for Volt-Var control using these inverter-based resources. So thanks to all of you researchers, and I will describe basically the microgrid here, and then I'll kick it over to Sanjeev to talk about the offline analysis. So the test bed here is a microgrid that was actually deployed and energized in 2021 on our system. It has 2 buildings on a WSU Spokane University campus involved in it. And each one of those buildings has 100 kW of rooftop solar. And those solar arrays are equipped with smart inverters. all of the assets on the microgrid talk to a microgrid control system, as I mentioned. So that's the system that we will be modifying in order to talk to the VVC algorithms. Right now, the microgrid control system, in addition to talking to all of the endpoint devices, inverters, battery controllers, building load controls, all of that, it also talks to our utilities distribution management system and a DER optimization software suite. But we are adding a connection to that as part of this project, and that will be between the microgrid control system and a new external Volt-Var control algorithm. So that's the piece of the field deployment that we'll be adding to what's existing out there, in addition to the modification of the inverter settings. So that's kind of where we're at from a demonstration site perspective. This is all the assets are up and running currently today. So we'll just be making these modifications as part of the pilot for UI Assist. So I will kick it over to Sanjeev to go through the offline scenarios.
Yeah, thank you, Mike. So how we actually plan for the testing of this offline cases, especially looking at all three types of VVCs. So we'll actually consider the one objective, just looking at the loss minimization or the VAR optimization, but actually we're focusing on the loss minimization of the case. And then we have a different test cases we propose around, like the base case, over voltage, under voltage cases, but actually we are going to present mostly the base case and the over voltage or under voltage cases. But the other case we actually tested is the CVR, the conservation voltage reduction application as well, but actually we are not going to show because of the time constraints. So the parameter wise, again, we are going to look at what are the system wise losses, what are the inputs and outputs of the each PV units, and what are the improvement at the local bus voltage as well as the across the system or the feeder. So we are only considering the feeder F7. We are not considering all the feeders coming from the third hatch. So you can see the simplified one line of the feeder F7, and that has an upstream substation, and then it will feeding all the way down to the microgrid that is connected on the same feeder. So then moving on, so just to show you like how exactly those looks like. So here there's some basic results projecting how the over voltage or how the under voltage looks like on a phase wise voltage, and you can see the base case, and then here the cases are simulated by just manipulating the load most of the times, and then in some situations we actually increase the DER capacity just to produce the over voltage scenarios. And then, like I mentioned, the two objectives we worked on, but we are going to present only the one of them in this slide. So then I'll quickly hand over to MIT to present distributed VVC scale.
Thank you. Just a sound check to make sure you can hear me. Okay, perfect. Could you go to the next slide, please? Great, thank you. I just want to go over our architecture first, and then we'll go over some of the distributed details and then into the results that we have for the AVISTA test case. So what you see here is an overall hybrid Volt-Var control architecture, and the idea behind this was to be able to integrate both inverter-based DERs that have that faster set point change and some of the traditional devices like capacitor banks or OLTCs. And for the work that we've done with the AVISTA, we focused only on the DER component. And so the results will only be looking at that distributed optimization happening at the 5-minute time scale. And we're basically doing a set point optimization. So we'll determine what the optimal set point is based on 5-minute forecast for load and generation. That will then be sent to a primary controller, and the primary controller will then do the regulation about that set point. Next slide. So what the optimization looks like in a framework, if we have this underlying grid model, we're looking at a 3-phase unbalanced optimal power flow. For the AVISTA test case, we did use a balanced system, but the model that we have is for an unbalanced system. And then we have our load and our DER constraints, and then voltage and congestion. This goes into our distributed optimization block, and so we're using the PAC algorithm, proximal atomic coordination algorithm. Basically, what this allows us to do is to take this global optimization problem, break it down into smaller components, and that problem is being solved at each of these nodes with some communication between neighbors. The output of that distributed optimization block is the optimal set point for our smart inverters, and we can add other resources like demand response and storage. Could you click next? There's just an animation. Great, thank you. So because it's fully distributed, we're able to get computational tractability for really large scale problems. And compared to other distributed approaches, we have reduced communication requirements and we're able to preserve data privacy. This is what the algorithm looks like. And if you click next, you're going to see just like a convergence plot to be able to show that we're able to satisfy our global constraints despite being fully distributed in computation. Next. So this slide is just going to animate through what the steps in our distributed VVC is going to look like. On the bottom, you see that timeline. So at t-1, t0, t1, you're going to see the different components of our optimization. So if you click next, if you just click through a couple times so I don't have to keep asking, thank you. Okay, so what happens at t-1 is that first step. We're preparing for optimization, and we're going to begin our optimizing at time t0. We're basically going to forecast all of our loads in our generation and estimate any flexibility range that we have. We have a pre-processing step that allows us to solve our optimal power flow problem in a much faster way, and so we go through that pre-processing. All of this happens in a distributed manner. It can happen centrally for certain resources if it's easier for AVISTA, for example, to forecast all of the loads across the network because they already have that data. That can happen as well. Then at t0, optimization is going to begin. The PAC is a iterative distributed optimization algorithm, and so you're going to have iterations at this faster time scale where I have k plus 1 denoted in orange. At every one of those time steps, we're going to do a local optimization. Then we're going to have some communication with neighboring agents. In this case, we're communicating the voltages at these nodes. And so you can see that it's asymmetric in where the information is flowing as per the orange arrows here. And then we're going to do another local update of dual variables and then continue. That happens every iteration. Now, once that algorithm converges, we're going to hit time t1, and that's 0.3. We're going to change the set point to that new optimal set point, and that's going to hold for time t1 to t2. And what you see is that once that set point is sent to the primary controller is then able to regulate about that set point. And we have our timescales so that regulation, the dynamics of that regulation decay much faster than the next set point change. Next. Great, thank you. So one of the key features of being able to do distributed computation versus centralized is being able to break these really large problem structures down into smaller problems. And so this is for our three-phase current injection model, what the size of that optimization would look like centralized versus distributed. So the number of variables is significantly smaller in the distributed optimization, so above 1,000 down to 50. The number of equality constraints and inequality constraints is also much lower. And the number of variable exchange is actually quite small. So it's only 10, 12 variables per iteration. Now, if you have a balanced model, that would be divided by 3, so it would only be 4 variables per iteration. And so that gives us a lot of kind of flexibility in how we're looking at our model. And for really large problems, that our distributed optimization can really be helpful. And on the next slide, I talk about some of the timescales of the optimization and what happens with the communication. So with the distributed architecture, we do have communication between agents, and really what the total time for convergence is going to look like really does depend on what that communication infrastructure looks like. So what I have in this table here is basically just a projection of what different types of communication infrastructure could be. If you have really slow communication, that's what the transmission grid has been using in the past, then we see kind of taking 5 minutes to go through our 1,500 iterations as an example number. But as we start moving towards kind of these critical IoT designs, as well as ultra reliable low latency communication, which are being developed and really would be where the future smart grid would be moving towards, we see much faster convergence times. So if we want to change our set point every 5 minutes, we can take 2.5 minutes and come down even to the seconds level to be able to get to that optimal solution in a distributed way. Next. I think next should be a summary of the results, and then we'll go into some graphs. So I know that this has a lot kind of going on, and I just want to put it here just so that we can see kind of what we were interested in. We have our base case, under voltage and over voltage cases, and then what we also did is we tested out a couple different control schemes. So whether we're playing with the power factor or we're just using the remaining inverter capacity to not adjust the real power setting, but only inject reactive power. And so I will say that some of these are better to just compare across rather than between the different cases. And so we have the losses in the network, the total real and reactive power injections on the second line, and then the third and fourth are the voltage magnitudes across the entire day, or the 95th and the 5th percentile voltage magnitudes. I think a lot of this is better communicated in graphs. So in the next couple of slides, we can look at those. If we can go next, thank you. So this is for the base case, and we're able to compare having no control, having power factor control, where the power factor can vary between 0.5 to 1, as well as having no real power curtailment, but all of the remaining inverter capacity can be used to inject reactive power. And so as you go across from left to right, you get more reactive power that's able to inject. And these results are really clear in being able to show that improvement that we can get. So we're able to push that voltage, for example, in the power factor graph up mostly in the middle of the day. And that's because that's when we have the most P generation. And the reason we're able to get much better improvement during the day here as compared to the rightmost graph is because we're actually doing a trade-off between reducing how much P is being injected and creating more Q. And that's because we're using power factor control. But if we're looking at the Q as per the inverter capacity, the benefit you see here is during those hours where you don't have any generation, we're still able to improve the voltage because the inverter can be used to inject some Q without injecting P at the same time. If we go to the next case, I think I have the undervoltage case. And so what we're looking at here is we're not injecting any real power. We're only using the inverters present for reactive power injection. And so here I'm showing two different objective functions, loss minimization and CVR. Generally, they look very, very similar in this undervoltage case. In the overvoltage case, which I don't have in this slide deck, but I'm happy to share separately if someone's interested, these actually do look quite different. And so even in this undervoltage case, we're able to get significant improvement if we have these inverter resources available in the grid and able to use. So if we go to the next slide, this is some of the detailed voltage results, also comparing different control strategies for the base case. And so if you see the blue is going to be the very bottommost graph, that's where you don't have any control. And as you slowly start moving up, that's how you have more Q that you can inject. And the anomaly, which we already talked about earlier, is that yellow line, which is where we have the power factor of 0.5 to 1. The reason you get much, much better improvement in that center period is because you're basically trading off P and Q, which isn't exactly ideal. So if a utility would not want to trade off P and Q, thus you can't get that performance without losing some real power injection. And instead, you're going to see something more like the red and the purple, which are very close to each other, actually, except that the purple, which is looking at the inverter capacity, gives you this boost when the sun is down as well. If we go to the next slide. So this one is really interesting because we're looking at two specific buses in the network. The one on the left has a little bit more variation in the voltage. The one on the right is a little bit more constant throughout the day. These are both two different PV buses on the network. And if you click next, we can zoom into what's happening in those time periods. And so the lines are a little thin, so the colors might still be hard to see, unfortunately, but we're basically seeing on the left-hand side that that's in the middle of the day where you have most of your real power generation and the sun is up. And so you see the performance depending on how you are determining the bounds of your reactive power and how much you can inject varying. But you see that regardless of how you do it, you do get improvement from having no control. On the right-hand side, you actually see that transition between when having Q inverter capacity during the sun being down is performing better into the power factor of 0.5 range becoming better in the yellow. And that's because the sun has come up. And so which control strategy is giving you a better voltage changes depending on what your needs are in that network. And I think the next slide is going to look at just a quick diagram of 5 different buses in the network. These are all 5 different PV buses. Here I'm showing no control in blue, in red is power factor of 0.5, and in yellow is that Q inverter capacity. And we basically see that the impact of VVC is very different across the entire network. So node 42, for example, sees the most difference in voltage improvement when we start using control. Whereas some of these other nodes, example 54 and 56, see very few differences. If you actually look at the scales on the graph, those scales are different on the y-axis. So the improvement you see in 42 is actually quite substantial, whereas 54 and 56 are actually quite small changes in the voltage. But this is also just kind of understanding that depending on where your resources are connected, where you place some of these voltage control techniques can be more important in that decision. So if you only have limited ability to control your inverter, 42 is probably the node that you want to be focusing on to be able to have this voltage control perspective. And I think that's my last slide, but okay, thank you. I'll hand it off to the centralized group.
Yeah, Subir, can you unmute and stuff? Yeah, Subir, I still muted. Yeah.
Yeah. It's just a quick sound check. Am I audible?
Yes.
Thank you. Can you go to the next slide, please? So the quick idea, I think I have presented this one before within the group itself. So just quickly, just to mention it here that centralized optimization techniques for especially for the volt techniques are widely well practiced stuff. And it's for this particular case. As you can see that we need basically in our case the network is basically modeled within the OpenDSS, and you need certain amount of information as you can see in that and the container box that you need the system topology, network impedances, controller parameters, and the controller objective. All of them have to be within the centralized controller, feeding back within that centralized controller, and you need the load and generation measurements coming all throughout the network. Has to specifically mention that you need all those measurements, and then the centralized controller calculates what the set point should be, and then feeds it back to the each of the individual DERs. As I will, Sanjeev, can you please go to the next slide? So this is the typically how it would look like. So everything is modeled kind of in MATLAB. So this is how the the network system topology and the impedance look like. One more slide. This is where the controller parameters should okay, so controller parameters should look like, and then the objective functions. As you can see that you have that option to toggle between selecting the whether you want to select the system-wide loss minimization or the CVR that we talked about in the as Sanjeev talked about. Next slide, please. So here we basically consider three-phase balance system for generating the set point, and we use the Diedesch equations for power flow equations, and we considered the objective functions as we discussed, the minimization and loss or the squared voltage magnitude deviation. So basically, squared voltage magnitude deviation is kind of used as a proxy for the CVR. And we use a quad prog for calculating the optimal bar set point. Here, quick few things I wanted to mention things here that it's a balanced system, but of course you can model unbalanced system, and then the computational, of course, given that the problem is because of the use of linear disk flow, our computational tractability and the computational time is pretty less. But as as we move as we increase the complexity of the system, the complexity the computation time is going to go up. One more slide, please. Yeah, as you can see here that so these are the information, the one in the maroon color that basically are within the database, and then the QLs and the PLs and the BGs, they are the reactive power loads, and then active power generation and the loads, these are the measurements, and that's one we talked about in the previous slide. Next slide, please. Yeah, next slide. Yeah, so as I talked about that, we talked about that here we are assuming that the controller is retroactive, so we don't need forecasts, and then the reactive power set points are kind of based on the previous measurements. But of course, so basically to ensure that the retroactive scheme, the deployment need to be in the faster time scale. We need to make sure that the previous condition still persists. Otherwise, it won't be the set points won't be appropriate. However, since given that this is a centralized scheme, I think AVISTA system would already have a forecasters with the centralized like ADMS built in, and that can be easily, easily taken together and then, use it as you want. Okay. And then the optimizer is fast due to the problem being convex and it's a polynomial time. And also we basically taken care of another aspect that if there is no feasible solution exists. So here we basically wanted to ensure that the voltages are within that hard bound. And if that hard bound is not being, if you are not able to satisfy, then we basically use the previously calculated var set points. Next slide, please. Here we wanted to show you that what we are trying to do here is that we are assuming that we are assuming that the active powers are not being curtailed, and what we also want to do here is that we assume that the converter capacities are pretty much given to us. Active powers are not being curtailed, so remaining capacity will be used for as and when needed for basically calculating the reactive power generation. So as you can see here that you already have active power generation input previously calculated, and then you have got the the capacity of each of the inverters, and then from there you can calculate what is the upper reactive power injection upper limit and lower limit. They are being fed to the optimizer to calculate what is the set point. So we have complete utilization of the DERs. Next slide, please. So here are a few slides showing that how algorithm performs. It's basically, this is for the base case scenario, and as you can see that the voltages, especially for what we have observed here is that in each of the cases, algorithm wants to push the voltage up, and we have observed that in almost all of the cases, which means that as if you go to the next slide, as you can see here which means that you need the reactive power supplying reactive power needs to be supplied locally, and if you go to the next slide, as you can see here that the algorithm works as intended, and you can see that the losses are being reduced because the objective is of course loss minimization objective. And if you look at the figure lower right hand corner, and as I was mentioning that if you wanted to reduce the network losses, it is it would be wise that you do supply the reactive power locally, and which is kind of the solution is kind of trivial, as you know. In certain cases, you are able to see that the losses improvement is marginal. That could be because of the scheme is retroactive. Plus, as you know, that in some of the cases, the reactive power injection capability of the DERs are being hit. So there are two aspects. Reactive power capacity of the DERs needs to be remembered, and the second thing is that the model is retroactive. So it may, so if that, as I mentioned you, that the algorithm has to operate in a faster time scale. If you do not have the forecasts, which could be compensated by the AVISTA CDMS. However, so because of those constraints, your improvement may not be all throughout. Next slide, please. So as Sanjeev mentioned, I'll just quickly gloss over this. As I basically quickly mentioned the last slide, that in each and every one of those cases, what we observed is that the voltages, the algorithm tries to push voltage up, and then the improvement is dependent upon what is the network condition. As you can see here, that the increased voltage profile is pretty much minimal. Next slide, please. Yeah, this is as I mentioned about in a previous set of cases. Next slide, please. Yeah, so I wanted to highlight here that this like the previous cases, the algorithm is able to reduce the system-wide losses, and one thing is that without needing to go through each and every slides, we have observed that the algorithm performs as intended, and the reduction in the substation flow and providing reactive power locally reduces the network losses. Next slide, please. I think next slide. I think it does not to be. They are Next slide, please. Next slide. Yeah. So we also observed that the losses are being reduced with our algorithm. And one quick thing I wanted to mention here is that as you have seen that the algorithm is pretty simple. It's easy to implement. You don't need forecasts built in, and it works at intended, and it can be easily deployed within a centralized location, and that's the benefit of it. And okay, yeah, that's all from my end. Thank you.
Yeah, thank you, Subir. I think I will. Yeah, Ben.
Yeah, alrighty. So I will be presenting the local VVC scheme from WSU. There's two objectives for our local VVC scheme. We want to first maintain system stability, basically making sure the voltage stays within healthy bounds. And the second is to optimize the power losses through Volt-Var control. And so the requirements for the local Volt-Var control is to have local measurements of bus voltage and the upstream feeder's current, and a smart inverter that's capable of receiving commands from our controller. The advantage of this local Volt-Var control scheme is that there's no need to set up communication, there's no need to set up a large communication network to collect data into one location, which is a lot of effort. And it does not require system modeling like topology tracking or anything like that. And measurement bias won't affect this because it's disturbing and perturbing, it's perturbing and observing the results. So the bias will just be overlooked through that. And it's because the lack of need to set up communication architecture, it's really easy to scale to a large power system. It's essentially like a function encoding that you can just apply wherever you have a inverter that's capable of receiving commands. Next slide. So the first objective is to maintain system stability, and that happens through adaptive droop control. So there are a few things that can change on the droop curve. So the Q max on the graph on the bottom left, Q max is going to be dependent on how much active power the inverter is currently providing. So if the inverter is a 100 kVA inverter and it's producing 90 kilowatts, you have a less capacity than if it's nighttime and the inverter is supplying 0 kilowatts. And so we can take that into account to optimize, or sorry, maximize the available Q just by observing how much active power is currently being used. And so this is a good point to talk about. One issue that we see is that the SMA inverters that AVISTA has, they do have Modbus registers as shown in the top right. There's more registers there, but I just cropped it to make sure it fit on the screen. But they do have Modbus registers that allow us to change the Q1, Q2, Q3, Q4, all those variables on the bottom right graph. But they come with a disclaimer saying that they shouldn't be changed cyclically. So we're still trying to figure out what cyclically means. it has to do, I think, with the volatility of the memory. When the inverter powers off, it needs to retain those set points. So I think it's something to do with that. I think that memory can wear out. But we are looking at the idea of just having the adaptive droop control happen in the software to change the Q set point going to the inverter. Next slide. And so the second objective is power loss minimization across the system. And so if we measure the upstream power and the bus voltage where the inverter is, then then the local algorithm at that PV inverter can perturb the system's can perturb its Q source that it's controlling. And so while it's perturbing the Q source, the current from the upstream is going to be changing because the voltage of that bus is being changed by the Q injection. And so when so this algorithm doesn't know where the minimum is, but the whole idea of it is it's searching for and finding the minimum. And so it'll disturb the Q, it'll try to raise the voltage of that bus, which we don't know what the gradient looks like. This is just an example. But say we try to increase the voltage of that bus, the I squared can start to decline. And you keep disturbing it and it keeps declining. Eventually, if you disturb the voltage even further, we've gone beyond the point of optimized, and now we start to increase the current again. And so the algorithm will recognize that it's past the optimum point. It notices that the current is getting larger that it sees coming from its upstream feeder, so it'll disturb it back the other direction towards the optimum value. And so this introduces the idea that because this local scheme is not taking global measurements, if you only have a few PV, if you have small PV penetration, you're only going to be able to achieve the localized optimization value. So wherever those PVs are, those loads near that will be optimized. But if you have high PV penetration, this local scheme will begin a little game of tug of war between all the buses where the PV are located, and it's actually able to achieve a pretty good global optimization value. And so that goes along well with this idea that it's easily scalable. As you introduce more inverters on your control system via batteries or PV, this scheme just gets more robust, it gets more able to do its job better. And the benefit of it is that since there's no communication between these controllers, it's easy to go beyond smaller areas. So it just takes like if you can distribute this with other parties, they don't have to connect together to grow. So many people can implement this system without having knowledge of each other, basically, which is easy to coordinate. There is none. Next slide. And so this is kind of a basic overview of what the code is doing. There is two loops. There's the extremum seeking loop, that inside loop. That's doing our optimization. And there's the outside loop, which is doing the adaptive droop control. The inner loop happens on a shorter time scale. It's between like 2 to 6 minutes. And then the outer loop can happen every 10 to 30 minutes. It really just depends on the tuning of the system. And so let's go to look at the extremum seeking real quick. We see that I squared, or basically what we're using as the S loss, gets passed in through the washout filter, which removes noise from the system. And then we add a sine wave on top of it. Anyway, so that extremum seeking section is what's adding the perturbation signal on top of our losses. And that ends up becoming, through the algorithm, we calculate a V reference, which we can use through the Volt-Var droop control function to create our QDP set point for the next time stamp. Yeah. And the outer loop. Anyway, so the outer loop is basically measuring the bus voltages, and it checks what it sees as nominal. If we see that we're on average below nominal voltage, it's going to adjust the droop curves to bring that bus back up as close to nominal as possible. So when there's other, when things happen on the system, like load is added or load is removed, we're able to pull it back up close to nominal, so that when other bigger events happen that might deviate the voltage, we're starting closer to healthy, so we have a larger range to deviate before we're unhealthy. Next slide. And so if this is kind of what it's not really communication architecture, but that's what the drawing is. And so I said that we have to measure the bus voltage and the upstream current of each inverter. And so we have two sets of inverters that we're looking at on this particular section of the microgrid, the left side and the right side. So in order to optimize the left side, we can take relay measurements from each one or from any of the three sources. And it just depends where you want to do the optimization. And so if you want to optimize a larger area, you go a little further upstream from the inverter that you're controlling. So those are just showing the options that you have to take measurements from that would do the job. Okay, yeah. And so the way, can you go back one more second? And so the way this would be implemented is the local Volt-Var control would be put onto a PLC like the SEL RTAC, and that PLC would sit somewhere near the SMA inverter, and just plug into the network switch that is near that inverter, and pull the measurements from that, and then it would be able to use the network to pull the measurements from the relay. Next slide. And so the person who was previously working on this project has used this as his dissertation, and these are some of his results. But if we look in the table, this is the IEEE 123 bus system with high PV penetration. He tested the system with a really smooth irradiance curve, like there's no clouds, and then he tested it with a really sharp irradiance curve, like there was clouds. And we see that the proposed method on the smooth solar radiation on the power loss, the proposed method had 770 kilowatt hours loss. But if we kept the V reference to just 1 per unit at each bus, the losses were 1,100 kilowatt hours. So that's a pretty significant gain in optimization. I'm not sure what centralized method he used, but he also ran it up against the centralized method. And where it didn't do as good of a job because it's not taking measurements from across the system, for the lack of coordination between the PVs, it still performed very well, and there's just significantly less work required in networking to make this local Volt-Var happen. And we see similar with the high variance irradiation. Next page. And so we're presenting two cases here, the base case and over voltage, but the aggregate 24-hour loss without Volt-Var control on the AVISTA system was 592 kilowatt hours. But with the local Volt-Var control, it was 543 kilowatt hours. So we've gained 8.1% efficiency on the system when we apply the local Volt-Var control. Next. So we looked at two buses in particular that were most I guess most susceptible to bus voltage change. So their feeders were a little longer or something. So the left side is without local VVC, the right side is with. And if we look at the minimum bus voltage without local VVC on the left, 27 East Main Ave, we see it go down to about 115 volts. On the right side, the minimum is about 116.5, just as landmarks that we can look at. And so it does improve the voltage across the PV nodes for the cases. Next slide. This is an easier way to look at the whole system in one graph instead of having to compare all those different slides, but just focusing on where I put that red box. Without local Volt-Var control, we can see that almost all of the bus voltages are sagging slightly below 120 volt nominal. These are measured on the low side where the PV is connected. But we see them all sagging a little bit below 120. But when we apply the local Volt-Var control, it's able to pull those almost all the voltages up to hover right around 120 volts. So that's the adaptive droop control, trying to fix the voltage to a more nominal value. Next. So this is, we're looking at the import from the utility and from the microgrid connection. So earlier we looked at that picture of the smaller area microgrid. That's the top two graphs. And then from the greater, just the utility to the whole area is the bottom two graphs. So on the left side, without the local VVC, we see that the microgrid is importing on average about 110 to 120 kVARs, that little orange line where the arrow is pointing to. And with the local VVC, we see that the algorithm decides to produce a lot of Rs from the available resource, which greatly reduces the amount of import Q from the utility source. Or sorry, across the microgrid's PCC. It's that difference is a little less noticeable on the utility. Next. Oh, and then just for reference, look at, can you go back one? Sorry, I thought of one more thing. So look how smooth the Q line is. This is, I believe this is due to the inverters having ample room to import or export VARs from the inverter based on the time of day. So it's able to quickly and smoothly find the optimization value. So if we go next. So this is graphs looking at the PV, P and Q outputs with and without the local VVC. On the left side, we see that it only shows measured kVA because Q is 0. So basically power, the only thing it's producing is power. On the right side with the local VVC, we see that the measured kVA is consuming the whole capacity of those inverters through a larger portion of the day. The left graphs show that it just barely touches the max rating of their inverter, but we're able to use more of the inverter's ability with the local VVC, but without exceeding the inverter's ability. So we see that in looking at the measured kVA lines approaching max kVA, but never passing it. Yeah, next slide. So this is the same system, just with an undervoltage scenario. Too little generation and too much load. But without the Volt-Var control, losses were 800 kilowatt hours. With the local Volt-Var control, losses were 767. So that's another 8.65% efficiency gain. Next slide. So just looking to see the voltage improve, we see that even in the undervoltage scenario, that the 27 East Main without the Volt-Var control was hovering right around 114 volts. This local VAR, with the local Volt-Var applied, it raised that voltage up to about 115.2 or 115.5 or so. So it was able to raise the voltage slightly, improving the system's ability to survive. Next slide. So again, just an easier picture to see the whole system. We can see through that red box that it does pull the bus voltages up closer to nominal. It's not able to achieve it quite as well. If we look in the local Volt-Var control, it sags a lot more in the middle, but it still was able to pull it up to a healthier state than without the local PVC. It's not able to pull the voltage up as far because in order to increase voltage, we have to supply more VARs, but the amount of VARs we supply is limited by the real power being produced during the middle of the day, because we prioritize the real power from the PVs. So the more real power there is, the less ability to produce VARs, the less ability to correct voltage. So that's why we see the bigger sag in the middle of the right graph than the base case. Next slide. So we see with the local Volt-Var control, this graph is less smooth than the base case, and I believe this is because the local Volt-Var control recognizes that it's unable to find the optimization value, but that's because there's less bars available to adjust the voltage to find that optimum value. So it just struggles a little bit more in the under and over voltage case, where there's less bound to disturb and observe. But it does still reduce the VARs import to the microgrid. Next slide. So in order to cause the undervoltage scenario, the P, I guess, let's see, we couldn't produce any power. And it's just, yeah, anyway, next slide.
Yeah, Ben, you can wrap up, sorry.
Oh, okay. Yeah, you just gotta move forward to the end of the presentation then.
Okay.
Anyway, yeah, we see that the VARs never reach the maximum capacity of the inverters, and they do increase the VARs in order to support the voltage. Next slide.
Yeah, that's it. Thanks, Ben. So just to give you a quick summary, like how exactly like each scheme is performing before I jump into that. So it's a common system we shared among each partner, and the system constraints as well as the parameters what we consider remain same. We have like 11 PVs which are distributed, and 9 of them are actually laterally connected, and 2 of them are on the primary side of connection from the microgrid side. And then we didn't even consider the voltage regulators and the cap banks. We just kept it idle in all these 3 algorithms and the test scenarios we performed. So, and then we come up with a comparison. Okay, how exactly each algorithm is providing an improvement compared to one another. Again, there is a different way to measure the losses in each scheme. So just to like let you know that why there is a significant difference exists between the algorithms. It all depends on how we determine the losses, but it's not the issue with how we model it or the how we actually consider the constraints wise, because all the system ratings and the line ratings and the load ratings have remained same for all the schemes. And then whatever we actually pre-populated the scenarios and then we gave it to them. So just to give you like how we are comparing it, we are comparing with respect to what are the inputs required. Okay, what are the inputs required for each scheme? So if, for example, if you take the inputs from the distributed VVC side, it's a forecasted load and generation node, especially like if you want to look at the primary control side, they need the voltage, nodal voltages. So it's again nodal voltage exchange between the agents as well as within the cluster. So within the agent area, so that is again internal to that. when we look at the centralized and local VVC, so the centralized is more on the generation, load and reactive power, like how throughout the network, because you're looking at the complete system level, and then how whether it could be aggregated or maybe the distributed ones, but they need the system level generation plus the loads. And if you look at the local side, it's more completely local to the system or the bus. So whichever you're focusing on, or maybe the PV unit that you're considering in. So it's only the bus voltage and the upstream current you're considering for the local VVC implementation. And the requirement of the communication side is the, okay, so the distributed VVC needs the nodal voltages and the communication between the neighboring agents or the areas. And then looking at the centralized is again, as you know, like it's a centralized means it's pulling the data from each assets, each VAR assets to the central agent, and that's where you're performing the optimization. So it's actually need the real-time feed measurements, and then it will dispatch the set point commands according to the optimization objective we are performing on. And then looking at the local side, so it is just the real-time measurement from the local PCC bus. It's not necessarily from the upstream or the other buses near neighboring buses. So. And then execution wise, it depends on the complexity as well as the model you're considering in. But based on this AVISTA system, what we come across is like seconds to minutes for the distributed side, and then 30 seconds to somewhere between 15 minutes. You can also execute for the centralized, and then for local, it is, I mean, it actually driven by the how you define it. It can come in the order of seconds, or you can, if you look at the secondary layer or maybe the final layer of the implementation side, it will be in the order of minutes. So it will be 30 seconds to the order of 15 minutes. It can vary. And now looking at the improvement side, so it's more or less should be similar, but like I mentioned, so it is difference exists the way the losses are measured. That's why you see some variation from one method to other method, but overall, like we see at least 2 to 8%, sometimes even more than 10% improvement has been observed in the losses. But if you look at the distributed side, because they consider the distributedly and then all the assets, so it is giving a much higher improvement compared to the others. The dependencies, again, it's the dependencies we mean is like what are the other external dependencies, like what is the factors that influences the performance of the algorithms, what we tested here. So the major thing is if we want to perform the CVR side of it, like we need the JIP modeling of the loads, because as of now we model all of the loads as a PQ. We didn't model any of them as a JIP load. And then the unbalanced nature, whether you're considering the unbalanced nature of the system or not, so that drives the complexity of the system. So then the third thing is like what is the penetration and the ratings are available, because it all depends on how much VAR it can produce and what is the amount of penetration you have it on the feeder. So those are actually the factors that influences the performance of each scheme here. Just to summarize what we actually done so far is actually we looked at the common test system and we performed like a over voltage, under voltage. Again, under voltage is more common because if you look at the fore end of the feeder side, and that's again which are not upgraded in nature, looking at like downtown areas or where the crowded areas which are still with the old infrastructure. And the over voltage is something like we thought of like, okay, if there is a really underloading conditions and where the high penetration comes up from the consumer side. So that's the intention we had it from the AVISTA. So we performed on those 3 cases. And along with these cases, we also performed on the CVR side. Like I mentioned, the CVR is more on the setting up to a fixed limit, but it again depends on the what type of characteristics of the load exists in your feeder. So it all drives the improvement from that direction. And now implementation side, we already discussed like what are the ins and outs and what are the requirement side. And the overall, like the benefits wise, we see the benefits from one to the other schemes. But again, looking at the implementation and then the feasibility of the feasibility of the scheme into the field side and how easily they can do it without altering any existing infrastructure. So that's what they criteria is. But then the AVISTA does not differentiate any scheme with respect to a certain conditions or the test scenarios here. It's just looking at the feasibility or the implementation requirement side. Now we are going to review. Now what we are going to do is like AVISTA is already reviewing it, what the schemes and what are the results they already have it. The next step is like we are already started the process for lab testing. Like we setting up the lab environment to test in different scenarios. And once the scheme is done, scheme is finalized, and then we are working on the embedding that scheme into the RTAG in a different language that's supported by the SCL RTAG. And we'll be testing in those scenarios in the lab scale, like a HAL hardening loop or power hardening loop simulations, taking the actual SMA inverter as well as the real feeder data from the third hatch, especially the feeder F7. And then after the going through all the performances and the case-wise analysis, then will be this scheme will be further given to the field crew to just deploy in a nearby or maybe in the PVSS from those two micro buildings. Yeah, that's all. Thank you. Yeah, we do acknowledge all the support from the AVISTA and all the partners here, and thanks for the funding from the DOE side on the USS. Yeah. Questions?
Yeah, well, we did really good because we did only 2 minutes late there. So thank you to the speakers for getting a lot of information in at one time. And there's been some dialogue in the chat. I think we can go maybe 1 or 2 minutes, but hopefully if any speakers have any attendees have additional questions, they can reach out to the speakers. But I think there was one question. Ahmed, did you get all your questions answered?
Yep. Perfect.
Okay. All right. So this is a really, really cool example of multiple different methods and now comparing it. And I think a real one of our real impacts of our work, demonstrating it from the R&D all the way to the test system, and now eventually working with AVISTA to get it on their system. So it's a very exciting part of our UI Assist. So we really appreciate all the speakers and great information, a lot of information at once. You may have to watch it on slow motion to catch up with everything because they did fit a lot in there. But I know if anyone's interested that all of these speakers, and one of the other things we might want to do is also ask our speakers if there are any papers that are specific for these, that we will Tiffany will capture those, and we can also on the next digest we send out next week, and also post some of those when we post the link on YouTube. So thank you, everybody. Thanks for the efforts, and particularly thank you to AVISTA for their working with us on this, and particularly Mike has spent a lot of time on this, and his team. So again, thanks everybody. And next month we will have seminars from some of our interns, our joint interns. So, and it'll actually be December 1st because of the it'll be December because of Thanksgiving week is actually the 4th time. So thanks everybody. Have a great rest of your week.
Thank you.